All right, let's explore. Number 10, the shadow biosphere. In 2010, NASA astrobiologist Felisa Wolfe-Simon published a paper in the journal Science that quietly proposed something extraordinary. Working at the edge of Mono Lake in California, a body of water with arsenic concentrations hundreds of times higher than safe drinking water limits, her team had cultivated a bacterium called GFAJ1 that appeared to do something no known life form should be able to do: substitute arsenic for phosphorus in its own molecular machinery. The implications were not immediately obvious. Phosphorus is one of the 6 essential elements of life as we know it, woven into the backbone of DNA itself. Every organism on Earth, from the simplest bacterium to the most complex mammal, uses the same basic chemical toolkit. That toolkit was assumed to be universal, the only possible foundation for biology. Wolfe-Simon's findings suggested the assumption might be wrong. The concept her work reignited had been developing quietly for years. Astrobiologist Paul Davies had written extensively about what he called the shadow biosphere, the possibility that life arose not once on Earth, but multiple times, producing chemically alien organisms that share our world without sharing our chemistry. Such life would be invisible to us not because it hides, but because every instrument we use to detect biology is calibrated to the life we already know. Later studies challenged the specific arsenic DNA claim, but the shadow biosphere hypothesis itself remains scientifically active. If a second tree of life exists alongside ours, using different molecular machinery, our standard biological tests would pass right through it. We would be living alongside something ancient and alien, sharing our air and water and registering nothing. What other forms of life might be moving through our world right now? Undetected, not because they are rare, but because we have never thought to look for them in the right way. Number 9. The flatland problem. In 1884, an English schoolmaster named Edwin Abbott published a slim mathematical novella called Flatland, in which two-dimensional beings live their entire lives on a flat plane, completely unable to conceive of a third dimension. When a three-dimensional sphere passes through their world, they perceive only a circle that appears from nowhere, swells, and vanishes. They have no framework for what actually happened. The book was presented as satire. Physicists eventually recognized it as a precise description of our own situation. The mathematical logic Abbott formalized has been developed rigorously since. Mathematician Charles Howard Hinton coined the word tesseract in 1888 to describe the four-dimensional equivalent of a cube, and the geometry of higher dimensions has been standard university mathematics for well over a century. The rules are not speculative. They are provable, and their implications are genuinely disturbing. A being with access to a fourth spatial dimension would relate to our three-dimensional world the way we relate to a drawing on paper. We can see every part of that drawing simultaneously, including its interior. A 4D observer would see the inside of every room, every container, every human body. There would be no wall, no lock, no skull capable of blocking a four-dimensional line of sight. Privacy, as we understand it, would simply not apply. If such an observer moved through our space, we would perceive them only as a three-dimensional cross-section, a shape that materializes, changes, and disappears without apparent cause. We would have no way of knowing we were seeing a fragment of something vastly larger, moving through an axis we cannot perceive. The mathematics does not tell us whether four-dimensional beings exist. It tells us that if they do, our entire concept of a hidden or private space is a limitation that applies only to creatures of our own dimensional level. Number 8. The Calabi-Yau dimensions. In the 1980s, physicists working on superstring theory arrived at a discovery that was either the most elegant solution in the history of science or the most unsettling. Their equations, which attempt to unify all the fundamental forces of nature into a single coherent framework, only worked if the universe had not 4 dimensions, but 10. The 6 extra dimensions were not missing. They were folded, compacted into extraordinarily small geometric structures that hide inside every point in the fabric of space. These structures are called Calabi-Yau manifolds, named for mathematician Eugenio Calabi of the University of Pennsylvania, who first conjectured their existence, and Xing-Tung Yau of Harvard University, who proved mathematically in 1977 that they could exist. Yau received the Fields Medal, mathematics' highest honor, partly for this work. The manifolds are compactified at approximately the Planck length, 1.616 times 10 to the negative 35 meters, a scale so small it is to an atom what an atom is to the observable universe. Physicist Edward Witten of the Institute for Advanced Study in Princeton unified 5 competing versions of string theory in 1995 into what he called M-theory, adding an 11th dimension to the framework. The resulting equations contain approximately 10 to the power of 500 possible solutions, each describing a different set of physical laws. Our universe is one solution among an almost incomprehensible number of alternatives. The 6 compactified dimensions described by Calabi-Yau geometry are not somewhere else. They are threaded through the interior of every atom in your body right now. Something small enough, or structured differently enough, could navigate those folded dimensions without ever touching the 3 we inhabit. If 6 dimensions are folded into every point in space, and we have no instrument capable of detecting them, what else might be folded inside them, moving through geometries we cannot measure, in directions we have no sense organ to perceive? Number 7. The brane world. In 1999, physicists Lisa Randall at Harvard University and Raman Sundram at Johns Hopkins University published a paper in Physical Review Letters that began as an attempt to solve a dry technical problem in particle physics. The hierarchy problem asks why gravity is so extraordinarily weak compared to the other fundamental forces. An electromagnet the size of your hand can lift a paperclip against the gravitational pull of the entire Earth. The answer Randall and Sundram arrived at was stranger than the question. Their model proposed that our entire universe, every galaxy, every planet, every atom, exists on a thin membrane called a brane, floating within a higher dimensional space they called the bulk. Gravity, unlike light and matter, is not confined to our brane. It leaks into the bulk, spreading across extra dimensions, and arrives at our world diluted and weakened. That leakage is why gravity feels so feeble. Our universe is losing gravitational energy into a space we cannot enter or observe. The disturbing implication of the Randall-Sundram model is its side effect. If our universe is a membrane in a higher dimensional bulk, other membranes could be floating nearby, separated from us by a gap that is unreachable by any matter or light we can generate. A second brane could be separated from ours by a distance too small to measure, yet completely invisible, because everything we use to probe reality, including light itself, is confined to our own membrane. The paper was published to solve an equation. It was not intended to raise the possibility of inhabited neighboring universes pressing silently against our own. But the mathematics does not distinguish between the two. Randall and Sundram's model remains one of the most cited papers in theoretical physics, and it leaves open, without resolving, the question of what might exist in the bulk beyond our brain. The Randall-Sundram model was designed to explain why gravity is weak. The answer it produced was that our universe is a membrane, and we have no way of knowing what is floating beside it. Number 6. The Pioneer Anomaly. On March 2, 1972, NASA launched Pioneer 10 from Cape Canaveral, followed by Pioneer 11 on April 6, 1973. Both spacecraft were sent on trajectories through the outer solar system, their paths calculated with extraordinary precision using the best gravitational models physics had to offer. For years, they performed exactly as expected. Then, as they crossed into the deep outer solar system, something began pulling them off course. The deviation was tiny, an anomalous acceleration of approximately 8.74 times 10 to the negative 10 meters per second squared, pointing back toward the sun. But it was consistent. It persisted across decades of observation data, replicated across both spacecraft traveling in different directions. Astrophysicist John Anderson and his colleagues at NASA's Jet Propulsion Laboratory formally identified the anomaly in a 1998 paper in Physical Review Letters, and for over a decade it remained one of the most closely watched unsolved problems in physics. The anomaly resisted explanation. Gravitational effects from known planets were ruled out. Dark matter distributions in the outer solar system could not account for it. Modified gravity theories were proposed and tested. For 10 years, the Pioneer anomaly sat in the scientific literature as genuine evidence that something was acting on objects leaving our solar system in ways our best gravitational models could not explain. In 2012, physicist Slava Turyshev and his team at JPL published an explanation. Heat radiating asymmetrically from the spacecraft's nuclear power source was generating a tiny but measurable push. The thermal recoil model is now the scientific consensus. A minority of physicists argue it does not account for all the data, but that position is not mainstream. What the Pioneer anomaly demonstrated, even in its resolution, is that our most carefully tracked spacecraft, monitored with precision instruments across billions of kilometers, showed a force we needed 4 decades and the full resources of JPL to partially characterize. The gaps in our understanding of physics in deep space are real, measurable, and capable of surprising us. Number 5. Dark matter's shadow. In 1933, Swiss astronomer Fritz Zwicky was working at the California Institute of Technology when he measured the velocities of galaxies in the Coma cluster and found something that broke his mathematics. The galaxies were moving far too fast. The visible matter in the cluster, every star and gas cloud he could detect, generated nowhere near enough gravity to hold them together. By any calculation, the cluster should have flown apart long ago. Something invisible, generating enormous gravitational force, but emitting no light whatsoever, had to be holding it in place. Zwicky called it Dunkel Materie, dark matter. For decades, the idea was treated with skepticism. Then, in the 1970s, astronomer Vera Rubin at the Carnegie Institution of Washington began measuring the rotation curves of individual galaxies and found the same problem in every one of them. Her landmark 1980 paper with Kent Ford in the Astrophysical Journal made the case definitive. Dark matter constitutes approximately 27% of the total energy content of the universe, outweighing all visible matter by a factor of 5 to 1, and it passes through everything. Estimates based on standard dark matter models suggest that approximately 100 billion dark matter particles stream through your body every second. They pass through the Earth as if it simply is not there. Despite this, direct detection experiments including LX Zeppelin, buried deep underground in South Dakota, and Xenon 1T, housed in the Gran Sasso Laboratory in Italy, have not caught a single confirmed dark matter particle after years of operation. The more disturbing theoretical extensions go further. Some physicists, including researchers working on hidden sector models, have proposed that dark matter may not be structureless. It may form its own atoms, its own chemistry, its own complex arrangements, in a shadow sector of physics that occupies the same space as our universe, but never interacts with ordinary matter. You are not a solid object moving through empty space. You are a collection of ordinary matter, interpenetrated every second by a river of invisible mass that does not know you are there, and that we have never, despite nearly a century of searching, managed to catch. Number 4. The simulation hypothesis. In 2003, philosopher Nick Bostrom at Oxford University published a paper in the Philosophical Quarterly built on a single probabilistic argument. He proposed that at least one of 3 statements must be true. Virtually all civilizations destroy themselves before reaching technological maturity. Virtually no mature civilizations choose to run simulations of their predecessors. Or, we are almost certainly living inside a computer simulation right now. The mathematics of the argument, which Bostrom laid out in rigorous formal logic, leaves very little comfortable middle ground. The simulation hypothesis is not a philosopher's daydream. In 2010, physicist James Gates Jr. at the University of Maryland announced something that had emerged from his work in superstring theory. Buried in the equations describing the behavior of fundamental particles were mathematical structures with the same architecture as error-correcting codes, the same type of redundant information checking used in data transmission systems. Gates raised the possibility, publicly and directly. The equations that describe reality contain, at their deepest level, a structure that looks like something was written to run reliably. Physicist Max Tegmark at MIT has argued for what he calls the mathematical universe hypothesis, the position that mathematical structures are not descriptions of reality, but are reality, with direct implications for the question of who or what authored the mathematics. Physicist Melvin Vopson at the University of Portsmouth published work in AIP Advances in 2022, arguing that information has measurable mass and that the universe may be a data processing system at its core. If a simulation runs, it is run by something. That something exists in an outer layer of reality that contains ours the way a programmer's environment contains the program. It has access to every variable, every particle state, every thought that has ever occurred within the simulation it maintains. If James Gates found the mathematical architecture of error-correcting code inside the equations that describe the behavior of matter itself, the question that follows is not whether that code exists. The question is who wrote it and whether they are still running the program. Number 3, the holographic universe. In 1997, theoretical physicist Juan Maldacena at Harvard University published what would become the most cited paper in the history of physics. The paper demonstrated a precise mathematical equivalence between two radically different descriptions of reality: a universe with gravity and 3 spatial dimensions, and a lower dimensional universe with no gravity at all. The mathematics showed they produced identical predictions. One of them, Maldacena's equations implied, might be the shadow of the other. The holographic principle underlying Maldacena's work had been developing since physicist Gerard T. Hooft at Utrecht University proposed it in 1993, and Leonard Susskind at Stanford University gave it formal development. Its most disturbing implication came from Stephen Hawking's work on black holes, which showed that the information content of any region of space is proportional to its surface area, not its volume. The 3-dimensional interior is, in some profound mathematical sense, redundant. Everything it contains is already written on its 2-dimensional boundary. In 2017, a team led by Kostas Skenderis at the University of Southampton published findings in Physical Review Letters, claiming to identify observational signatures consistent with a holographic origin in the cosmic microwave background, the oldest light in the universe. The paper was contested, as frontier physics always is, but it represented the first serious attempt to find empirical traces of the holographic structure in real cosmological data. The holographic principle, if correct, means that our 3-dimensional reality is generated by information encoded on a 2-dimensional surface at the edge of the observable universe, approximately 46 billion light-years away. We are not the source of our own reality. We are the projection, and the surface that encodes us has access to everything, every particle, every interaction, every moment, because in a rigorous mathematical sense, it is not watching us from a distance. It is us, written in a language 1 dimension simpler than the one we experience. Whatever writes on that boundary does not watch us from the 4th dimension in the way an observer watches a scene. It writes us into existence from it, and the most cited paper in the history of physics has not been able to prove that this is not what is happening. Number 2. The quantum observer. In October 1927, the greatest gathering of physicists in history convened at the 5th Solvay Conference in Brussels. Niels Bohr, Werner Heisenberg, Albert Einstein, and 24 of their contemporaries had come together to confront a result from quantum mechanics that none of them could explain away. The double-slit experiment had demonstrated, repeatedly and without ambiguity, that a particle fired at a barrier with 2 openings behaves as a wave, spreading across both possibilities simultaneously until the moment it is detected. Observation, somehow, changes what physically happens. The Copenhagen interpretation, which Bohr and Heisenberg formalized, made the claim precise. A quantum system does not have a definite state until it is measured. The wave function, the mathematical object that describes all possible states simultaneously, collapses into a single, definite reality at the moment of observation. Einstein refused to accept this, famously insisting that God does not play dice. The experiments continued to prove him wrong. Physicist John Wheeler at Princeton University later formalized what he called the participatory universe, the idea that observers are not passive witnesses to reality, but are in some sense necessary for definite reality to exist at all. Wheeler's delayed choice experiment, confirmed by V. Jacques and colleagues in a 2007 paper in Science, demonstrated something even stranger. The choice of whether to observe a particle can apparently influence its behavior at a point in time before the choice was made. In 2019, a team led by Massimiliano Proietti at Heriot-Watt University in Edinburgh published results in Science Advances, showing that 2 observers can make irreconcilable but equally valid measurements of the same physical event. Objective reality, at the quantum level, appears to be observer-dependent. The many-worlds interpretation, proposed by Hugh Everett in his 1957 Princeton doctoral thesis, offers an alternative that avoids the collapse problem by proposing that every quantum event causes the universe to branch, with every possible outcome occurring in a separate reality. This does not resolve the mystery. It multiplies it by infinity. If reality only becomes definite when it is observed, and the universe has been crystallizing into definite states for 13.8 billion years, then something has been doing the observing for the entire history of time. Physics has never been able to define what qualifies as an observer, and that failure, quiet and persistent, and largely undiscussed, is the most unsettling open question in the foundations of science. Number 1. The conscious universe. In 1932, mathematician John von Neumann at the Institute for Advanced Study in Princeton published the definitive mathematical formulation of quantum mechanics, a work so rigorous that its framework has never been superseded. Buried inside the proof was a conclusion so disturbing that most physicists have spent the 90 years since trying to argue their way around it. Von Neumann demonstrated mathematically that the chain of physical causes involved in any observation has no natural stopping point within the physical world. Every measuring device is itself a quantum system, requiring measurement by another device, which requires another, and so on without end. The regression can only be terminated, von Neumann concluded, by something outside the physical chain, by a conscious observer. Physicist Eugene Wigner at Princeton formalized this into what became known as Wigner's friend in 1961, a thought experiment showing that 2 observers can hold mutually contradictory but equally valid quantum descriptions of the same event. In 2019, Massimiliano Proietti's team at Heriot-Watt University tested this experimentally and published results in Science Advances, confirming that observers can indeed measure irreconcilable facts about the same physical occurrence. The problem is not philosophical, it is empirical. Physicist Roger Penrose at Oxford and anesthesiologist Stuart Hameroff at the University of Arizona developed orchestrated objective reduction, a theory proposing that consciousness is not a product of brain chemistry, but a quantum process occurring in protein structures called microtubules within neurons, making mind a fundamental feature of the universe's physics rather than an emergent accident of biology. Physicist Henry Stapp at Lawrence Berkeley National Laboratory and former CERN researcher and philosopher of mind Bernard Kastrup have published peer-reviewed arguments that idealism, the position that consciousness is the fundamental substance from which reality is constructed, is the most mathematically parsimonious interpretation of quantum mechanics available. This is not mysticism. It is a conclusion forced by the mathematics of the most successful scientific theory in history, arrived at by researchers at some of the most prestigious institutions in the world, published in peer-reviewed journals, and never successfully refuted. It is a minority position within physics. It is also a position that no one has been able to prove wrong. If consciousness is not produced by the universe, but is instead the fabric the universe is produced from, then the fourth dimension is not a spatial axis. It is awareness itself, the ground of reality, the thing that collapses possibility into existence. And if that is true, then what has been watching us from beyond our three dimensions, generating definite reality out of quantum probability for the entire history of time, is not something alien or external. It is the deepest layer of what we are, looking at itself from a vantage point we can never occupy, because we are always already inside the view. John von Neumann did not set out to discover that consciousness might be fundamental to reality. He set out to write the mathematics of quantum mechanics, and the mathematics wrote that conclusion for him. If you want to see more videos like this, click the video on screen now and make sure to subscribe.